The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, so for number 2, we just need to state the theorem used to deduce that our sequence is convergent and find its limit. So you have a theorem in your book that says every bounded monotonic sequence is convergent. So we need two conditions. We need bounded and we need monotonic. So remember what these two terms mean. A bounded sequence is one that is always less than a particular value, or if it's a decreasing sequence, it's always greater than a particular value. In other words, there's a limit to how high the sequence can go, or how low the sequence can go. We just proved that in part B of number 1. We said that our sequence is always less than 3, so it's definitely bounded. So we have that. A monotonic sequence is a sequence that's either always increasing or always decreasing, and that's what we proved in part 1, part A, that our function was always increasing. So we have that this sequence is bounded and monotonic. If it's bounded and monotonic, the theorem is that it's a convergent sequence. So we know that our sequence A sub n is convergent, and finally for part 3, we need to find its limit. Okay, so there's a couple of different things that we can do to find the limit. We know that the limit of a sub n as n goes to infinity and the limit of a sub n plus 1 as n goes to infinity need to be the same. So limit as n goes to infinity of a sub n should equal limit as n goes to infinity of a sub n plus 1. Because as you're going to infinity, adding one term in the sequence doesn't do anything. Now this right here is what we're going to call L. We don't know what that is. We're trying to find the limit of the sequence. So we get that L must equal the limit as n goes to infinity of a sub n plus 1. However, we know that not only should this equal L, but we have a formula for that. We can make that a little bit easier. So a sub n plus 1 is actually 3 minus 1 over a sub n. And remember that your limit operator distributes over any operation here. That means the limit as n goes to infinity of a sub n, this number is actually going to be L. So we get the following limit there. L equals 3 minus 1 over L. And now we need to solve that. We need to solve for L. Excuse me. So there's a couple different things we can do here. The easiest way to do this would probably be to multiply everything by L right off the bat. So we'll get L squared equals 3L minus 1. That gets rid of the denominators, makes it a little bit easier to work with. You can see this is turning into a quadratic equation. So we get L squared minus 3L plus 1 equals 0. So we need to figure out which of these it is. So here we have, we're going to need to use the quadratic formula because this is not factorable. So opposite of b is 3 plus or minus the square root of b squared, so we have 9 minus 4 times 1 times 1 all over 2. So what we need to be careful about here is that we have two possibilities, but only one of them is going to be right. So we have 3 plus or minus the square root of 5 over 2. Only one of those is going to be right. We need to determine which. Well, the problem here is that root 5 is a little bit bigger than 2, and if we do 3 minus that and divide by 2, we're already at a number that's lower than 1. But we knew that our sequence started at 1 and it was monotonic increasing, so there's no way out of these two possibilities, it absolutely could not be 3 minus root 5 over 2 because that's already lower than 1. Again, we started at 1, increasing sequence, so it certainly can't be that, which then only leaves 3 plus root 5 over 2. So that is our limit of our sequence as n approaches infinity.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.